name is Peter Dowdorf from Atkins Realis. In this video, I will show you how to use the SAGIS Lakes model. This was developed as part of the broader development work that created the SAGIS-SIMCAT system for Ukwear. In contrast to the river modeling, the SAGIS Lake model is part of the SAGIS code, whereas the river modeling makes use of SIMCAT, as you have seen in previous videos, and this forms the basis of the river simulations. So why might we want to model lakes in the SAGIS-SIMCAT system? Clearly one reason is that you may be interested in water quality in the lake in relation to WFD standards, for example. However, another reason is that lakes can have a big impact on downstream water quality in rivers. Lakes can remove chemicals by settling and other processes, and also the flows downstream can be greatly modified. Therefore, modeling the lakes is also a way to improve how the rivers are represented. Before going into the details of how the lakes model works, we'll first look at how the lakes and reservoirs are represented in the SAGIS system. There is a layer called SimLakes, a polygon layer, and within this layer is information on all the lakes in the model. This model has 5 lakes. All WFD lake water bodies are included in this layer within the regional databases in England, Scotland, and Wales. There are 2 types of lakes. There are online lakes connected to the river system. We can see an example here. I'll just zoom in. As we can see, the river passes through the first lake. This asterisk shows the inflow to the lake, and then the blue asterisk shows the outflow to the lake, and then it passes on and flows through the second lake. These rivers are represented in SAGIS-SIMCAT. We have now moved across the model to look at an offline lake. As you can see, there are no rivers running through this lake, no inflow nodes. There is an outflow node here that releases the flow back into the river. Another feature you can see is this shape, which is the local catchment to the lake. This is represented by another layer called Sim Local Lake Catchment. These features are optional. There is another way to represent the catchment of these offline lakes that I'll show you later. Another important consideration for SAGIS lake modeling is that in contrast to the rivers, there often needs to be refinement of the lake features. This is because these have not been routinely modeled in the same way as the rivers by the Environment Agency and others. So when you start a lake study, you may need to first consider if the lake is represented in the correct way. For example, in this case, there might in fact be a river in the real world running through this lake and then feeding into the river beside it. It is only designated as an offline lake because none of the SIMCAT SAGIS river reaches run through the lake. You might therefore consider adding a new river reach to this model that runs through the lake, along with an inflow and outflow feature. Or if the lake is really not that important, you can leave it as it is. Before going on, I would like to point out one other important feature on how lakes are represented in SAGIS. Many reservoirs in England, Wales and Scotland are pump storage reservoirs. This means they receive a lot of their inflows via an intake from which water is pumped across. In this example, water is transferred from this abstraction point, this intake, across to another lake over here to the west. There are many abstraction features in a SAGIS-SIMCAT model, but to specify that this feature sends its water across to this lake, we need to look at the attributes table in SIMFeatures where this abstraction is represented. I'll just open this up. If we move across this table, we will find a field called Target WB. We enter in this field for this feature the water body ID for the lake to which we wish to transfer the water. The specified amount of water that is abstracted from the river at this location is transferred across to the lake. This water has the water quality that is simulated by SIMCAT at this location. This can be as an annual average. If we look across, we can see this number is defined in this field here, or we can specify monthly values in these fields here. The final point about abstractions is that water can be abstracted from a lake. This is defined by an abstraction feature located within the lake, as we can see here. It knows that it's taking water from the lake because of its location on top of a lake polygon and between an inflow node and outflow node. We are now going to look at some of the information, data, and settings that need to be entered for each lake before we carry out a simulation. This information is contained in the attributes table of the SimLakes layer. Let's quickly look at this. We can see information in the various fields for each lake. Each lake in this case is a row of the table. Another way to look at these settings is to select a lake and then go into SAGIS and then click on Lake Settings. This form shows some of the key information and settings for the chosen lake. For example, we can see here in this box, it specifies, as we mentioned earlier, that it's an online lake. Here is the water body ID that we referenced before, the lake name, area, and volume. All of this information should already be within the SAGIS-SIMCAT model, but may need to be checked and refined, as I mentioned earlier. For online lakes, the catchment area around the lake is defined by the length of river reach running through the lake compared to the overall river length within the water body. This proportion determines how much of the water body load of chemicals goes into the lake. However, for an offline lake, you can specify a local area. For example, it could be 1 kilometre squared. If the overall water body is 5 kilometres squared, it will take 1/5 of the loads from this water body and move it into the lake. This is an alternative approach to the use of a catchment area specified in the SIM local lake catchment that we saw earlier. If a catchment is defined, this takes precedence over the local area defined in this box and in the attributes table that this references. The next thing I'm going to show you on this form is the output type. After you run the lake model, the simulated water quality and outflows are then fed back into the river into the SIMCAT model. Now this can be done in different ways, and this is defined in this output type drop-down box. If we select statistics, this means a distribution of water quality based on the lake simulation we fed into the river model. Whereas if we pick monthly file, a monthly file will be created representing the monthly pattern of lake water quality and outflows, and this will be fed into the SIMCAT river model. Or if we select MPD files, We'll create an MPD file with 1,000 shots that represent the distribution of water quality in the lake and the distribution of flows. We will now look at the options. If you click Exclude, this will exclude the selected lake from the lake simulation, and no outputs will be fed into the downstream river model. Now we'll look at Run Detailed. The SAGIS Lake model can be run in two ways: a simple model and a detailed model. In the simple model, the outputs represent a steady state condition. For example, if you imagine the lake model runs for many years, it will finally reach a steady state when the outputs for 1 year are pretty much the same as the outputs for the next year. In the simple lake model, the starting conditions do not change the model outputs. In addition, in the simple lake model, the inputs from the various sectors, such as livestock, wastewater, etc., are input to the lake in a simplified way. The default condition in SAGIS-SIMCAT is to run the simple lake model. However, if we click on Run Detail, a detailed lake model will be run for this selected lake. This produces monthly outputs over the period of the simulation. This period is defined in the simulation period box, so we could increase this to 100 years, for example. In this case, the starting conditions affect the start of the simulation, but change over time, diminishing as the simulation continues towards the end. Finally, we'll look at the dynamic sediment option. If we tick this, the sediment concentration during the simulation will change toward a dynamic equilibrium with the water column. This option is important if we wish to consider the impact of the sediment on delaying lake recovery. For example, in many lakes, historical loading of phosphorus can have this effect. Only the detailed lake model can take into account these sediment interactions. So why might we wish to run simple lake models for some lakes and detailed lake models for others? The primary reason is that the detailed lake model can take quite a long time to run, perhaps 10 to 15 minutes. In models where there are many lakes, there are 50 to 100 in some of the regional SAGIS-SIMCAT models, this would result in very long run times. Normally, we would run the detailed lake model in cases where it is the lake water quality that is of primary interest, for example, in relation to WFD targets. Otherwise, for example, if the main interest is to better represent downstream water quality, the simple model may suffice. We're now going to look at the chemical settings. These are process rates that determine how water quality changes over time as the simulation proceeds. There are rates for the three chemicals within the model. The first one to consider is the settling rate. This determines the rate of the loss of chemical into the sediment, in effect, a loss from the water column, through processes such as settling and absorption or uptake by biological processes. You can see there is a settling rate and a settling rate UB. The UB is an upper bound. In the detailed lake model, when the simulation takes place, values are sampled between the lower bound, which is the settling rate, and the upper bound. This allows you to incorporate parameter uncertainty into the simulation. The sediment release rate is a re-release rate from the sediment, usually at a slower rate than the settling rate. And again, there is an upper bound as well. Finally, there is the burial rate. This is the rate of loss from the sediment pool that cannot be returned to the water column. Again, with an upper bound. As I mentioned, the upper bound only applies in the detailed lake model. In the simple lake model, the settling rate, sediment release rate, and burial rate are used with no upper bound. Another setting under chemical settings is the sediment concentration. This is the concentration in the sediment pore water at the start of the simulation. And again, you see we have an upper bound. If the dynamic sediment box is not ticked, this concentration will stay the same throughout the simulation. Whereas if it is ticked, it will change over time to form a dynamic equilibrium with the water column and the permanent loss from the sediment. Finally, there are some boxes in which you can enter information on the groundwater quality of water that passes into a lake from groundwater as specified in these boxes. This is only likely to be important in a lake that is known to be fed by groundwater. In many lakes, these processes are known to be highly seasonal. For example, in shallow lakes, phosphorus is commonly released at a high rate during the summer. To simulate these processes, we need to vary the rate seasonally. This is done by first clicking on the Mon Rates button, which opens a form in which for each chemical you can vary the settling rate and upper bound and the sediment release rate and upper bound between the months. For example, if it's clear that phosphorus is being released at a high rate in the summer, you might raise the sediment release rates to a higher value during this period. When you're finished changing these rates, simply click on Apply for them to be saved by the model. These boxes below the rates can be used to set seasonal profiles. If you put a 1 in this box, it will return the same value for each month. If you raise it above 1, it creates higher values in the summer. And if we reduce it below 1, it does the opposite to this, creates lower rates in the summer. When we use these buttons, the average value for the monthly rates is the same as the annual rate set on the main form that we have seen previously. These can, however, be changed manually and then applied. I am now going to show you how to run the lake model. Before we do this, we have to run a version of SIMCAT that includes the information that the lake model needs. To do this, we go into SAGIS, create SIMCAT, but then click on Lake Inputs before creating the SIMCAT DAT file, which then has to be run. Once SIMCAT has been run, we then go into Run SIMCAT, select the DAT file, and then tick on Process Lakes, Estuaries, and Coastal Outputs, and click on Run. This transfers the information from the DAT file, but also the SIMCAT run outputs to create a table with all the required inputs to the lake model. We then go back to run SIMCAT, Again, select the DAT file, but this time tick Run Lake Model and click on Run. This opens a dialog box. You can remove or add chemicals, and then click Run. This will run the lake model. The lake model can take several minutes or longer to run depending on the balance between simple and detailed lake models. When it runs, it creates two types of file. One shows the steady state outputs, and another shows time series outputs. These files are written to the folder that contains the original DAT file. We'll look at these files now. The steady state output file has the letters SIM, SIM, added to the name of the original DAT file, .csv. Here we can see under deck code there are outputs for each chemical. This is ammonia, this is orthophosphate, and for each month. The values under month 13 are the annual statistics. We are now looking at the time series outputs. This has the letters SIMTS added to the name of the DAT file, .csv. Here we can see there are values for each month and each year going through the simulation. SAGIS provides a way to look at these outputs. Simply go to Excel Graphs and then select Lakes. Select the chemical you're interested in, and then the lake, we'll look at number 2, then the sample point, 2, and then click Run. An Excel sheet will appear. All you then have to do is click on the Initialize Lake Data button. When you do this, this will load data from the lake model output files into the spreadsheet. This automatically takes us to the monthly charts. We have monthly values for the simulated concentration in the water column, the monthly profile broken into sectors, the lake volume, and then a profile of the lake inflows and abstractions. If we change to a different lake, we just need to click on these boxes. So we can pick Lake 2 in this case, and this will show us the outputs for another lake. And now we'll look at the time series outputs. To do this, we go to the See Yearly Charts button and click on this. This takes us to the time series charts. Here we see the simulated concentration in the water column along with the 10 and 90 percentile. See how it changes with time. Likewise, in this chart we have the sediment concentration. The initial high concentration set at the start of the simulation has reduced. This chart shows the sediment flux, which is the proportion of the input of the chemical that comes from the sediment. So we see a seasonal pattern here, also a change over time. The final chart is the pattern of daily inflows and abstraction. And just a reminder that these outputs will only be available for those lakes for which we have selected the detailed lake model. Once the lake model runs have been completed, you can feed these back into the SIMCAT River model. To do this, click on SAGIS and then create SIMCAT file as before. Tick Lake Outputs and click Run. This will create a SIMCAT DAT file, but this time it will see that there are lake outputs in the same folder as the SIMCAT DAT file. As a result, information on the chemical loads from the lakes and the flows will be entered into the DAT file and then be incorporated into the river simulation. When carrying out lake modeling in the SAGIS-SIMCAT system, an important point is that the lake model and the river model are separate. So for example, if you wanted to look at these lakes in this part of the model, we can see two lakes in series on this river. Once we have run the lake simulation, we will know the outputs from this lake to feed into the river model, as we've just seen. However, we'll only know the inputs to the second lake once this second river model run has been carried out. And then if there were another lake downstream, we'd have to carry out this second model run of this lake model and then run this in SIMCAT to know the inputs to the third lake. Therefore, to run a simulation on a series of lakes correctly, it may be necessary to run both the lakes model and the river model several times. Finally, before ending this part of the video, I would like to say a few words about calibration of the lake model. Unlike the river model, there is no automated system for calibrating the lake model. Consequently, we have to run the lake model, look at the outputs, as we have seen, then go back into the lake settings to change the process rates, and then run the lake model again, look at the results, and then repeat the process iteratively, a manual calibration. In this process, we do not need to run SIMCAT again. We just need to run the lake model again, make the adjustments, and look at the outputs. The final thing that I am going to show you is another way to view the lake outputs and something called the trophic summary. It's important to note that the trophic summary will only work if nitrate, total phosphorus, and ammonia are included in your list of determinants. Once the lake model is run, we go into SAGIS, then plot outputs, then plot lakes. You can create outputs at the sample points or the lake centroids, and then also click on Trophic Summary and click on Create Map. This will create new output features on the map and in the table of contents. As we can see, a new layer has been created for each of the determinants, and these layers contain annual statistics for the model output. For example, if we look at total phosphorus, just open the attributes table, we can see a range of model outputs. Each row in this case is a lake. The symbology here is for the mean concentration. Now we can look at the trophic summary. This is presented in the form of a new layer called trophic summary, a feature for each lake on the map, and if we click on one of these, this form appears. For the selected lake, this provides some key information related to the trophic status. Here we have some general features of the lake. This summarizes the diffuse nutrient inputs. This the point source inputs. And this section determines, based on the nutrient inputs, the retention time, and the depth of the lake, which element is likely to be limiting for algae. In this case, it identifies N as the limiting chemical. If now we look to the bottom part of the form, this shows observed concentrations of nitrate, total phosphorus, and chlorophyll, and their confidence limits. The information on chlorophyll is in the data tables within the regional database. And then below this, we have predicted concentrations of nitrogen, total phosphorus, and chlorophyll based on input loads of nitrogen and phosphorus. These predictions are based on empirical relationships developed by the OECD in classic lake studies that form the basis of understanding trophic status in lakes. The form also shows the classification of the lake based on these values, along with whether or not it meets the WFD target. A legend for the classification is shown below. The primary purpose of the trophic summary is to allow the user to assess the trophic status of the lakes based on the outputs from the river model without having to go through the complex process of lake modeling. This also provides a kind of ground truthing of the lake modeling because the trophic summary is based on an empirical analysis with real lake data. We have now come to the end of this video on the SAGIS Lakes model. I hope you found it interesting and have success with modeling lakes. Thank you.